Okay, I think we're good to go. Excellent. Right, so this is a screencast of the lecture which covered the shear forces and the bending moments diagrams introduction. So the lecture covered drawing a shear force diagram and drawing a bending moment diagram. It covered the conventions that we're going to be using, and we looked at the problem where we had a beam with just concentrated loads. I'm going to do a teeny little bit of flip learning, which will be reinforced in your tutorial session, where we'll be looking at uniform distributed loads. So don't worry, because that will come part of your tutorial for the flip learning. So I'm going to call, let's reduce my size. I'm going to call shear force diagrams SF and bending moment diagrams BM. So, bit of a Halloween theme there. Why are we bothered about these bending moment shear force diagrams? Well, guys, we're going to talk about that, what will seem like much later. What we're really interested in is this bending moment diagram, because that tells us where the maximum bending moment is happening in a beam, and the maximum bending moment relates to something called bending shear stress. Okay, so when we're trying to bend something, it causes a lot of shear at a certain point in the beam. We can also pick up, it's almost like a kind of stepping stone to get to my bending moment diagram, the shear force diagram. The shear force diagram really for a beam isn't particularly of structural interest, because our forces, I'm pushing a force up here, or action say, and then a load here. So you can see the distance between the reaction and the load isn't going to create much shear. There's this big gap between the two. So in a structural sense, in terms of just a beam analysis, that isn't the reason why we're looking at that. It's more to get to this stage here. So that's what we're really interested in. More on that later. For the shear force diagram, this is found by taking the algebraic sum of forces. Well, we'll take vertical forces, we're only looking at them, and we're taking the sum of them that's left of a position x. So I'm going to take imagine the leftmost position of my beam, and then I call that x equals 0, and then I'm going to scan through my beam. So I'm going from left to right position across the beam. That's going to be my x equals 0, and then I'm going to scan across to my x equals whatever the length of the beam is. And as I'm going across, I'm then always going to look leftwards of that x position, which I'm going to call xx, and you can see, we'll see why in a moment. And I'm going to add up the forces. I'll be taking upwards as positive, and then plot them out like a plot as I move across that beam. The symbol that I'm going to use for this graph is going to be called Q, and that will have units of probably kilonewtons or maybe newtons. okay, because we're adding up forces. So in this lecture here, we're just looking at the concentrated forces, and the reactions are going to be forces and the loads are going to be forces. So they are the only two things that we're looking at. The next one, where we do a little bit of flip learning, is where we're looking at UDLs. Okay, so that wasn't covered in the lecture. For this particular case, if you imagine if this was let's say a solid UDL, well, if we're summing up forces to the left of it, initially there's going to be no force to the left of it, as I sort of start at that position there, I suppose. But then I'm going to hit my first reaction, and so I'm going to see a reaction, and then as I just move past the reaction, I'm going to get this sudden peak. Okay, and then as I move across, so that's my first reaction. Now as I move across, I'm going to get the load force, and it's going to slowly bring down my plot further and further as I go across. So it ends up causing a sloping straight line. But as I said, we're not doing that problem in this particular lecture. We'll come back to it if that's not making sense, so don't worry too much. And for my sign convention, so we need to have some cool music, because we're going to have a cool sign convention, as I was describing, that we will have that if the force is going upwards, so I've got my beam, I've got a load here, say of 10 newtons, and then we're going to have two reactions here, 5 newtons there, 5 newtons there. And the convention we'll be using is that if, let's choose a different pen color, if we've got the force pointing that's going upwards, we'll go up 5, move across, and then as we go past this force here, we're going to drop 10. So that makes me minus 5. As we go across, and then when we get to the end there, we're going to go up again 5. So if the force is up, I go up. If the force is downwards, I go down. Force up, I go up, like that. So here's my problem 1. So I've got 1 meter. So x equals 0 at this position here. And when x equals 1, we've got this downward force of 20 kilonewtons, and then, well, 1 plus 3 is 4, so when x equals 4, we're at the end there. So I've worked out the reactions for you, 15 and 5. Okay, so what am I going to do? So I'm going to do a plot where I look at my forces. I'm going to imagine an x position, which is going to be x-axis. I'm going to look at my forces left of that, and I'm going to sum them up, and then I'm going to plot them as I move along the beam. So I've pre-prepared this. So this beam, well, I should have put my units on there. So is going to be measured in kilonewtons, and then the next thing is, as I said, we want to imagine that we're going to put our x position. You can see why it's called x-axis now. So we put a nice line all the way for the beam, and we just look left. So we're only looking left of this beam to see what we can see. And what can I see? All I can see is this 15 kilonewtons there. So the first thing that's going to come on my graph is 15, assuming that I'm working in kilonewtons. Okay. So there we go. We've moved up to the x position. There. All I can see is 15 kilonewtons. It's a positive, so it's going to go upwards. So that's why we went upwards there, because it's a positive value. And but as I move my X position along, that's what I can see up to I get to point B. Now what happens when I hit point B? Well, the question is what happens when I move just a little bit right to point B and start looking back to my left? Well, what do you think is going to happen? So if you just go a little bit past point B, you can then see the 20 and it's coming downwards. So initially we're at 15, and now we're going to have the 20 coming down. So 15 take away 20, what's that going to give me? It'll be -5. Okay, and then I can imagine that I'm going to move my X position, my double X line, a bit further right. Let's say we can move it, I don't know, pretty much to the center of the beam and then look left. What would happen there? Well, all I can see is these two forces, one going up, one going down. Overall I've got a -5. And when I get to the end, well, what I've got to imagine is I've just gone a little bit to the right of the end of the beam there. So when we've gone a little bit right, then that means that we're going to have an upwards 5. So that means we're going to end up at 0 there. And hey, it's 0. Is this magic? I don't know. No, it's not magic. If I sum up my forces in the y direction, okay, by the time I got to the end of the beam, I should have 0. So it's not magic, it's what I expect to happen. Right. So I'm going to look at this problem here. Let's have a quick little bit of revision. Can I work out the reactions? How will I do that? Well, take that to be my pivot. I'm going to sum up my moments at A. Go around clockwise. So what we're going to have, we're going to have 120 times 1. Then we're going to have plus 40 times 3. And then we're going to have minus, how far we got? We've got 4 meters. So 4 r dy. Looks like a P, r dy. So r dy equals what? 120 plus 120. I make that 240. 240 divided by 4 gives me 60. So that should be 60. Overall I've got 160 going downwards. So 160 take away 60. That should be 100. Okay, should be able to do them that quick. Yes. Right, so we've got 100 on this side, 60 on this side. Now let's draw our shear force diagram. So stage 1, let's plot up our y-axis and our x-axis. Maybe I should be putting that this is x. I'm going to measure it in terms of meters there, really. And we're going to imagine we're some position between A and B, where that's my X position. Got double X line. Going to look left of me and see what forces I can see. What can I see? What I can see is that 100 going up. So at 100 and it's going upwards, so it's a positive number. 100. So up to this point, all I can see is 100 going up. Now let's move just a little bit right of this load, this 120 load that's being applied there. And now what can I see? Well, we've got the 100 going up, I can see now 120 going down. So 120, 100, and then we're going to go down 120. That will take us to be minus 20. 100, take away 120 is minus 20. Nothing much will happen until I get to go past the C point there, and when I go past the C point, I'm then going to drop a further 40, so we're going down another 40 there. So we're going down another 40, so we've got minus minus 20, take away another 40, gives us minus 60, and now we're sort of kind of around this position here, aren't we? And then we've got to imagine we've just gone a little bit right at the end of the beam, and then we come back to 0. So we're always looking, I haven't plotted it here because I've got the axis, but we're always looking starting off at 0 and then ending up at 0. Let's do that in red so that matches my plot. So we're starting off at 0 there, and then we're going to end up at 0. And if we haven't ended up at 0, you know you've done something wrong. So in the lecture I asked, we did some turning point tests, so this was the first one that we tried. Could you tell me what the shear force plot should be if I'm located at 0.5 meters from the left? So that's roughly around this position. You've got to look left of you and say to yourself, what force have I got left of me? Is it a positive? Is it a negative? What's it going to be? Have a think about it. Have you thought about it? Okay. The answer is minus 2 kilonewtons. Okay, because here I am, should be a little k there. Here I am, left of me, all I can see is this 2 kilonewtons. It's going downwards, and my convention is if it's going downwards I'm going to use a minus, so we've got minus 2 kilonewtons. That one was straightforward. What about if we're at 3 meters? So if you've got a problem like this, you probably just want to roughly indicate, yeah, that's roughly 1 meter, 1 meter. So roughly 3 meters is going to be there. Then I'm going to look left of that position. So there we go. So we've set our XX position there. Look left of us, what can we see? We can see 2 going downwards, 3.333 going upwards, and then 3 going downwards. So what's that going to give me overall? Overall, it should be a negative number, and it's going to be minus 1.67. so try that yourself. We've got 3.333, it's going to be recurring, and then we've got take away 5. So overall, can you see that's going to give me a 1.6 whatever. So here I've done it to 2 decimal places. Yeah, okay, I'm sorry, I used 3 decimal places there. But okay, so the question is, if I gave you a shear force diagram like this, do you think then you could produce the shear force? I'm sorry, if I gave you a illustration of a beam with the loads and the reactions like that, sorry, could you produce the shear force diagram like this? And the answer is yes, you can. Now for the tricky one, the bending moment diagram. So the bending moment plot is defined as the algebraic sum of moments acting to the left of the x position we're looking at, where we're going to treat the x position as if it's a moving pivot going across the beam from left to right. This time we're going to use symbol M related to the for our bending moment plot. And now we've got to decide on a convention. So for our bending moment diagram, we're expecting there to be a continuous line. The bending moment diagram will be a straight line between these concentrated loads that we're looking at. When we come to look at UDLs, we will start seeing curved lines appearing, but we won't be dealing with that during this lecture. The sign convention that we're going to use when we're looking left, so we've got to imagine that we're at some sort of pivot on our beam, and we're looking left, and the sign convention is that if we've got a force, maybe like a reaction force here, coming from underneath, we're going to treat that to be a positive moment. And as I look left, so that's my distance to this particular force here. And then if I've got a load coming downwards, and then I'm going to measure the distance to that load there, that I'm going to treat as an anti-clockwise moment. Now, depending on the conventions that you use, and different textbooks will have different approaches, and different university courses will have different approaches, so be careful when you're looking on the web or whatever of things, is that this particular convention leads to, if you have a positive bending moment value, you're going to have a sag in your beam, whereas if you have a negative bending moment, you're going to end up with a hog. So what do those terms mean? So a sag is where I imagine I've got a pivot there. I'm going to have got my beam here, and then I'm going to put a load on top. And what will happen for that? Well, you're going to end up with a smiley face. So that's sagging, okay. And then the hogging, well, again, we've got a beam here, pivot there, and then we've got a nice long beam, more like a kind of table arrangement. And where do you think I'm going to put my weights? Well, I'm going to put them here and here. So push down the loads on the ends, and what will happen then? Well, we end up with an unhappy face. But the beam in the middle is going to deflect upwards, and that's called a hog. Okay. Problem one's come back, but this time we are going to be using the bending moment diagram. So we're not doing a shear force diagram, so we've got to imagine we're some place along our beam, some x position. So I'm going to choose just an arbitrary position between A and B here, and this is my pivot that I'm looking at, and I'm going to see what force can I see left of me. Well, there's only one force I can see left of me, and that's this 15 kilonewtons. So I'm going to measure my distance from there to there. Well, that's just defined as that, since x is going to be defined, x equals 0 is going to be defined as this point. This point here is going to be x. Okay, so the moment is just going to be 15 times x. Is it positive or negative? Well, the convention is we decided that if it's going to be clockwise, it's going to be positive. So this is going to cause a positive moment. So we've decided to call these M. We've got the force 15, and we've got the distance x, and we have got a plus for positive moments. So that's our three components. We've got the force, the distance, and our sign convention, and that one's going to be positive. So nothing's going to change provided we get up to the B position. When we move past the B position, then something will happen, won't we, to it? Because we've got that then, as we look left, this load force coming down that we can see is going to create another moment. But provided I'm in that region A and B, then this formula here is going to be valid. So I'm just going to plot m against x, and it's just going to be a nice straight line. When x equals 0, m will equal 0. So that will be the same up to I get to the position B. I'm just going to have a nice straight line like that, and it will end with m equaling 15 kilonewton meters when we get up to the B position. So what happens when we move slightly to the right of B? Well, I've still got a distance of x from here to the original force that I was looking at, but now I've got this downward force, and I need to know what this distance here is from here to here. So what's that going to be? Well, the way to do that is to measure this distance, which I know is going to be 1 meter, and then say, well, this distance here is going to be the distance to x, take away the distance to the position of the force, and then we're left with this distance here. So the distance from here to here is going to be x take away 1, so x minus 1. Right, so x minus 1 will be the distance to that force. Now that force is going downwards, and we've decided in our convention that's going to give me a negative moment. So now let's put both the moments together. So we've got this one, so that's going to give me the plus 15 times x, and now this force here is going to give me a negative moment. It's 20, and its distance from to the pivot to that position is x minus 1. Nothing will change now until we get to the end. So again, we could stop in the middle and maybe look at what is m going to be equal to when I'm slap in the middle. Don't forget my beam is 4 meters long, so the middle is going to be when x equals 2. So I can substitute in x equals 2 and plot that on my graph and see where I am. So put in x equals 2, that will give me 30, and then I'm going to get minus 20 times x equals 2, so x take away 1 is 1, and so that's going to give me 30, take away 20, so I end up with 10. So when I'm in the middle, I'm going to end up with a value of m equals 10 kilonewton meters. Okay, so there I am. And when I take it all the way to the end, nothing will change. So we take it all the way to the end, and then let's plot what we get for the value of m when x equals 4. So when we're at the end of the beam now. So our equation that we're using doesn't change. Let's just put in our new numbers. So you've got now 15 times 4, so 60. And then we've got 4, take away 1, that's 3. 3 times 20 is going to be 60. So we've got, remember our sign convention will give us a minus there, so then we end up with 60. Take away 60 means that we're going to end up at 0. Now, am I surprised? My beam's not rotating. So when I sum up the moments going across the entire beam, the moments must equal 0. So no, it's not surprising the fact that our moments start off at 0 and then they end back up 0 for beams. Now let's come back to problem 2. Let's do the same sort of thing for problem 2. So we're going to start off imagining with some x position there, going to look left of us, going to measure the distance from here to here, and create my m. Now when we have more complicated problems like this, it's a good way to tackle these problems to consider these as sections. So we've got an A to B section, a B to C section, and a C to D section. And a good approach is to find what the M equation is for each section, come back, substitute numbers, and then start building up your graph. So that's a good way to do it. So imagine we're somewhere between A and B. We're going to look left of us, and then we're going to see what equations we're going to have, values we're going to have in our M equation. So between A and B, we're going to have that M equals, well, it's a positive because it's going upwards, so that's positive. It's 100, and it's a distance x. So when I'm in position somewhere between A and B, my equation for M is going to be plus 100x. Now when I'm somewhere between B and C, what we've got then? Well, we've still got this stuff going up, so that's still going to give me the 100x, but now we've got this thing here coming down. So we've got to measure this distance, and you notice there's a little kind of rule here that we're following. So what you need to do is measure that position and say, well, that's going to be x equals 1. And what you can do is then put that into brackets. So you have, open your bracket, x, take away 1, and that's where the 1's coming from. Close the bracket. So that's going to give you your distance back to the B position. And then when you're at the B position, you look for its false value. And then you look to see which way it's going. It's going downwards, so it's minus. So that's what the formula should look like when we're in between B and C. What about when we're in between C and D? Okay, well in that case, we've got the fact that we've still got this one, we've still got this one, but now we've got another one here to deal with. How far is it from its x equals 0? So it's going to be 3 meters away from x equals 0. That's where it's happening. So this distance here is going to be x take away 3, and that will give me my distance from here to here. It's going to have a 40 value, and it's going to go downwards. So we'll open the bracket, we'll put x take away 3, close the bracket, that's giving me my distance. Now I'm going to look for my false, so that's going to be 40. Then I'm going to see which way it's going downwards, so it's going to be my minus. So for my between C and D position, my M equation is going to be all of this stuff here. Once you form those equations, then it's a good idea to go back and then substitute in the values of the start and end positions. Normally you only really need to bother with the end positions. When x equals 0, we know m equals 0. You can see that. So the first thing you want to do is stop when we get to the end of the AB region, and the AB region ends at x equals 1. So I'm going to substitute x equals 1 into my equation, so that gives me m, open bracket 1, and that will give me 100. So that's what I'm going to plot. So I'm plotting 1, 100. Okay, so now I go back and look up what the equations I worked out for my BC region, and I work them out to be this. Nothing changes between x equals 1 and x equals 3. So what I'm interested in is plotting this position here. So I'll go back to my equation and I'm going to substitute in x equals 3. So 100 times 3, take away 120, open my bracket, 3, take away 1, close my bracket. So that gives me 300, take away, what's that going to be? I make that 120 times by 2, so that will be 300, take away 240. So there we go, and we end up with a value of 60. So then we're going to plot the value 360 there. And as a final check, always a good thing to do is to go to your CD region. So we're at the last region here, but just to check it, put in what happens when x equals 4, and it should go back to 0. So here we've got our equation that we're going to use to plot in this region. And now we're going to plot the final position, so when 4 and what value we're going to get. So we're going to get 100, take away, I don't know, 360, take away 40. So what will that be? So 400 take away 360 take away 40 equals 0, and there you go, bang, we've hit the 0 again. So that's a thing that we can use to check that we're getting the right result. Now then, let's see if you can find what the bending moment thing that we need to plot if we're at position 0.5 meters from the left. Pause the video if you like and work it out, and then carry on. So pause now. So the first thing you want to do is put a rough line there, measure this distance. So what's that distance going to be? 0.5. Look for your force and decide on your sign convention. So I make that should be a 2 times a 0.5, and it's going downwards, so a -1. So there you go, that's the answer, -1 kilonewton meters. Okay, what about if we're 4 meters away? So this time again, put a rough position where your pivot's going to be, so this one doesn't count. So we've got this force going down, so I need to measure that distance. That's going to be a 2. Then I've got this distance here, so I've got 3 meters, and that force is going up. And this one from here to here, that'll be 4 meters, and it's going down. So what we need to do is to find the m value at that position. It's going to be what? -3 times 2. Then it's going to be plus 3.333 times 3. And then it's going to be -2 times 4. So I don't know, -6. 333, that sounds like it should be 10. And -8 there. So I make that to be a -4, unless I made a mistake. Yes, I got the answer right. So there we go. I'm happy. The question was, do you think you could produce this bending moment diagram if I gave you these forces? Let's play that again. Yes, you can. Right, so that's it, I think. Coming to the end. So I'm going to be putting up a lot more shear force diagrams and bending moment diagrams. I'm going to do a tiny little bit of flip learning for how kind of pre-flip learning. We will cover it in your tutorial, provided you go to your tutorial, of how to deal with shear force and bending moment diagrams when we have UDLs, because that's the next thing that we need to cover. Okie dokie.